Hello, today we talk about the p-n junction. In this chapter, we talk about the construction of the p-n junction. As you see from this picture, we have a p-n junction which consists of the two pieces. One piece called a p-type and another is a n-type. Why this chapter is important? We say that after completing this section, you should be able to the first one, describe the diode and how a p-n junction is formed. The second, discuss the diffusion across the p-n junction and explain the formation of depletion region, define barrier potential, and state the barrier potential for silicon and germanium. And now let me see what we mean by the p-type and n-type. As you know that the p-type is a piece of intrinsic semiconductor which doped by the donor impurity atoms like a boron, and this added impurity atoms add a hole to the structure or to the semiconductor. And the n-type is also a piece of silicon or any semiconductor, impurity semiconductor, a pure semiconductor, was doped by the impurity atoms such as antimony, and this adding of impurity atoms add free electrons to the structure of the semiconductor. What is the p-n junction? So, if we have a piece of intrinsic semiconductor and we add or we doped aside by donor impurity atoms like in this picture, this add free electrons to the structure, and if we add acceptor impurity atom to another side, this add free holes to the structure, and then we get a p-n junction. As you see from this picture, we have a line junction between the n side and the p side, and by this we can get the p-n junction. At the first moment of the fabrication of the p-n junction, as we said, we added donor impurity atoms to the n side and acceptor impurity atoms to the p side. Therefore, we get free electrons in the n side and free holes in the p side. And then by diffusion, because the concentration of electrons in the n side large and the concentration of holes in the p side is large, therefore electrons from the n side go to the p side by diffusion process. Because of gradient in concentration, we said that the concentration of electrons in here is larger than the p side, therefore electrons go to the p side by diffusion. And also about the holes in the p side also go to the n side across the junction by diffusion process. Each electron go from the n side to the p side across the junction, left behind it a positive ion in the n side and create a negative ion in the p side. By passing a more number of electrons from the n side to the p side and also holes from the p side to the n side, we get a large number or greater number of the positive ions in the n side and negative ions in the p side, as we see from this picture. And then a region created which is called the p depletion layer or depletion zone. And if we reach a specific point, this positive and negative ions create a potential difference between them and then suppress passing any else electrons from the inside to the p side, and also holes from the p side to the inside, and we reach an equilibrium point. At this point, a potential barrier created in the depletion layer, and this potential barrier or potential built-in voltage depend on the type of semiconductor and the temperature and also the rate of doping. Therefore, we see that we have two p-n junction. First situation, we have a p-n junction at the first moment before the formation of depletion layer, as you see, and also we have a p-n junction after formation of depletion layer. The term of depletion layer refers to the fact that this region of this zone is depleted from the free carriers, electrons or holes, and there are just positive ions and negative ions, which they are bound charges. You see that in the depletion layer, as you see in this picture, this depletion layer do not contain any free carriers or electrons or holes. It just contain bound charges or bound ions. Therefore, it's called depletion layer. It means that depleted from free carriers. The potential barrier, or the potential difference of the electric field across the depletion region is amount of voltage required to move electron through the electric field. This potential barrier or potential difference is called the barrier potential. It means that we have a barrier against the moving of electrons from the inside to the p side, and also for moving holes from the p side to the inside. And let we see how we can define or how we can calculate or determine the width of the depletion layer, because the width of depletion layer consists from two parts. The part of it located in the inside, which we denoted by Wn, and another part located in the p side, which we denote by the Wp. And this is equal to root square of 2 epsilon Vb over Q multiplied by 1 over Na plus 1 over Nd. When the epsilon is a dielectric constant, and Vb is a built-in voltage, Q is the charge of electron, and Na is the concentration or the rate of doping of accepted impurity atoms, and Nd is the rate of doping of donor impurity atoms. Therefore, if we know the Na and Nd and the type of semiconductor, we can determine the width of depletion layer. And this is an energy band diagram of the p-n junction before formation of depletion layer and after formation of depletion layer. As we see from this picture that we have a p-n junction, the energy diagram of p-n junction, which consists of the EV, N, and this AVP, also it's the ACN, sorry, and this is ACP. We see that the electrons at first time, 3 electrons in the conduction band of the inside can pass through the p-n junction to the p side by the fusion process, and also holes can go from the p side to the n side by the diffusion process under the effect of the gradient in concentration of these current carriers. And this passing electron-free carriers from side to side, it goes to creating a depletion layer, and it's also goes to the creating of a potential barrier. This potential barrier, this amount is equal to E is equal to AVB. And therefore, by creating this potential barrier, electrons from the conduction band of the n side cannot pass or go to the p side, because it needs an energy, an amount of energy which is equal to E to raise and go from the n side to the p side. And it's also about the holes in the valence band of the p side, which they need an amount of energy to go to the valence band of the n side. And it's also the energy band diagram of the p-n junction. We see that electrons from the conduction band of the inside, these electrons need an energy to go to the conduction band of the p side. If there is no exist of this potential barrier, the electrons of the conduction band of the inside can go from the conduction band of the inside to the conduction band of the p side by diffusion process, and also holes in the p side, the valence band of the p side, go to the valence band of the inside by the diffusion process. And the direction of the diffusion current inside the p-n junction is from p to n, and it's from the n to p outside the junction. But minority carriers, they are electrons in the conduction band of the p side, and holes in the valence band of the n side can go from the p side to the n side under the effect of electric field, and also holes from the n side to the p side under the effect of electric field. And the direction of the drift current is from n to p. It has an opposite direction for the diffusion current. This is for drift, and this is for diffusion. As you see from this picture, that the diffusion current direction is from p to n side, and drift direction current is from n to p side inside the junction, and from p to n outside the junction. And now let we derive or derive the built-in voltage or the barrier voltage inside the PN junction. We know that we have a minority current carriers and the majority current carriers. In the inside we have this inside of the PN junction we have majority current carriers, they are electrons, and we have majority current carriers in the P side with they are holes. And there are minority current carriers electrons in the conduction band of the P side and minority current carriers holes in the valence band of the N side. Majority current carriers in the N side with their electrons called N sub N, and the minority current carriers in the P side with their electrons called N sub P. If we have a relation between the majority current carriers of electrons and minority current carriers of electrons, we mean if we have a relation between N of N and N of P, we know that N is equal, and we mean the equilibrium carrier concentration. N is equal to N sub C, which N sub C also equal to 2 V2 pi KT M effective over H square 3 by 2 EUS minus, if we go here, EUS minus EC minus EF over KT. Therefore, N sub N is equal to 2 pi M star KT over H square was 3 by 2 EUS ECN minus EFN over KT. And also about the N sub P, instead of ECN and ECF in here, we write ECP and EFP. Therefore, NP is equal to 2 multiplied by 2 pi M KT over H square was 3 by 2 EUS ECP minus ECF EFP over KT. Therefore, we have N of N over N of P is equal to exponential EFA minus EFP over KT, because ECN equal to ECP and they are eliminated. Then, as we take this relation for holes, also we get Pn over Pp is equal to this amount. Then we have that EFN minus EFP equal to EVB. Therefore, N of N over N of P is equal to EVB over KT. But from the law of mass action, we have that Ni square equal to N multiplied by Tp. Therefore, if we take this relation for a P side, we have P sub P multiply n of p equal to ni squared. Therefore, n of p is equal to ni squared over p sub p. By substituting the value of n of n in this equation, we get NAND over NI squared equal to E with EVB over KT. Then, if we take the ln for both of sides, we get VB equal to KT over E, then NDN over NI squared. We see that the barrier potential or the built-in voltage is depend on the temperature of the semiconductor and also the type of the semiconductor and the rate of doping impurity atoms for the semiconductor.